For this pattern of the Pythagorean's theorem, we see we have a expression that looks like u squared minus a squared, and so that being the case, since we have a subtraction sign here, this value for u must be the hypotenuse. It must be the largest value, because if we subtract the value a from it, we should still get a positive number, so this has to be a hypotenuse. And so that means the u is on the hypotenuse, and we typically like to put the constant then on the adjacent leg. It just makes for a nicer substitution in terms of substituting out in terms of secants and tangents, and again for setting up that ratio. So if we would set up the secant theta here, setting up cosine would be adjacent over hypotenuse. It would put this in the denominator, but secant's hypotenuse over adjacent, so it makes for an easier expression then, and you'd get the same expression if you set up cosine, but you just get the expression a little quicker if you set up secant directly. So we end up having the expression for secant theta here, and then since we have an expression that involves secant theta, we want to set up then an expression that involves tangent theta as well, because those two trigonometric expressions are related through trig identities. And so the opposite leg ends up being the radical then, and so you can set up tangent as opposite over adjacent. And when we set up that tangent as opposite over adjacent, opposite side being the radical, adjacent side being the value a, then when we solve for the radical, we get the u squared minus a squared. Then we get a tan theta here. So to set up the right triangle for this problem here, we're going to go ahead and get our right triangle set up here. And with our angle and our right angle symbol, and we know that this is our hypotenuse, so we have x on the hypotenuse, and we have this squared, so we need a 2 on the adjacent leg, which leaves then the difference of those two squares as the opposite leg there. So as we're setting up tangent theta, as we're setting up secant theta, we know that it's hypotenuse over adjacent. So the value for x then is 2 secant theta. And then we can go ahead and take its derivative. So the derivative of secant theta is secant theta tan theta d theta. And then we also need an expression for the radical here, so we can go ahead and set up the tangent of theta. And that is equal to opposite over adjacent. And so to get an expression then for the radical, all we have to do is multiply each side by 2 to get that expression for the radical. And just a quick oversight here. Get rid of that squared. There we go. Should be just x squared minus 4 on the opposite side there. So now we can go ahead and substitute out our differential dx. We can substitute out an expression for x, but we will have to cube it. And we can go ahead and solve and substitute out an expression for our radical. So once we put all of that in the integral here, we have our expression for x is 2 secant theta. We have to cube that because we have x cubed in the numerator. Our expression for dx is 2 secant theta tan theta d theta. And our expression for the radical in the denominator is 2 tan theta. So if we kind of tidy that up and simplify it, we have 2 cubed, which is 8, times 2, which is 16 in the numerator. We have 2 in the denominator, so I'll just leave that as 16 over 2 for this step. And then we have secant to the 4th theta, because we've got secant cubed times secant, and tan theta in the numerator. And in the denominator, we have tan theta. And so when we go to simplify this, we can go ahead and cross out a tan theta in the top and in the bottom. And we have 8 secant to the 4th theta d theta. So we have a secant to an even power. And so back from our secant tangent rules, we know we're going to save a secant squared. So if we save a secant squared, we also have a secant squared left over to convert. So there's our saving a secant squared. We're going to convert that other secant squared to 1 plus tan squared theta, using that identity from the last section. And then we can go ahead and do our u sub. So we're going to, again, we've substituted from x to theta, and now we're going from theta to u. So we have a few substitutions to do at the end, but u is tan theta. And when we take the derivative of tan theta, we get secant squared theta d theta. So this substituted out then looks like 1 plus u squared du. That's a nice integral to work with. So we have 8, and then we're just integrating with respect to u. So we have u plus 1/3 u cubed. Now we're going to go ahead and put in our trigonometric functions. So u is tan theta. And so we have tan theta plus 1/3 tan cubed theta plus c. And now if we come back up and get our diagram that we set up at the beginning of the problem, there we go. To reference that, then we can go ahead and we can set up our tangent ratio, so that's opposite over adjacent. So that ends up being x squared minus 4 over 2 plus 1/3 times the quantity x squared minus 4 over 2 cubed plus c. And at this point, you could probably stop with that expression, or you can go ahead and simplify that. We can distribute the 8 here, so we end up with 4x squared minus 4 plus, and we have an 8 in the denominator and an 8 in the numerator, so we end up with x squared minus 4 to the 3 halves power over 3 plus c.